Now, although we have the components, expressions for the components for both the tangential and the normal components of acceleration, it's really very desirable to have these expressions which depend only on the initial position function, or the position function, I'm sorry, and derivatives of that position function. Because typically we're able to find the position function, so it'd be really nice to discuss these components only in terms of this one function. Now we can actually do that using dot products. If I take a look at the velocity dot acceleration, that's going to equal v t dot v prime t plus v squared kappa n. Now, where did that all come from? Well, velocity you said we could represent as the magnitude of velocity times the unit tangent vector. So this right here is nothing more than my velocity vector. And earlier we said the acceleration can be expressed in terms of the tangential and the normal components, and that's exactly what I did. So I just simply rewrote this dot product using these representations for both the velocity vector and the acceleration vector. Now, when I carry out this dot product, what I'm going to end up with is v prime t dot t plus kappa. See, v squared is v cubed, and I'm going to have t dot n. Now remember, these are all vectors. Now when I look at this, remember these are all unit vectors. So the magnitude of t is 1. So the dot product is really a multiplication of the magnitude. So 1 times 1 is 1. So this is really nothing more than v prime. And then I have plus kappa v cubed times t dot n. Well, this is 0. This component right there has got to be 0 because they're orthogonal. If I look at that again, the unit tangent is here. The normal vector is here. These guys are orthogonal. That's the way we defined them. So the dot product of two orthogonal vectors is always going to be 0. So v dot a is really nothing more than v times v prime. So I'm going to write that as v dot a equals v prime. Now remember the tangential component for acceleration, a of t, equals v prime. So with that, I can say that the tangential component is really nothing more than v dot a divided by v, because that is equal to v prime over v, which is obviously just v prime. So I have this representation, but this is actually equal to, well, see, v is the first derivative of r, dot acceleration is the second derivative of r, divided by v. V is the magnitude of the first derivative of the position vector. So now I have the tangential component in terms of nothing but derivatives of the position vector. Now an, the normal component, is the curvature times v cubed. Nope, v squared, I'm sorry. And curvature we defined before as simply being equal to the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. But now I need to multiply this by velocity. So when I multiply by velocity squared, well, velocity squared is r prime squared, because r prime is velocity. Well, that's going to cancel here. So I'm going to get this normal component as being really nice. It's simply r prime cross r double prime divided by the magnitude of r prime. Therefore, I can write acceleration, this acceleration vector, which is still a function of t, is going to be r prime of t dot r double prime of t over the magnitude of r prime of t times t plus the magnitude of r prime cross r double prime divided by the magnitude of r prime times the unit normal vector, which we shouldn't have to put these on. Again, these capital letters, when you see them, you know what they are. So there we go. Now I can think in terms of acceleration and only think of it in terms of, or at least the components, tangential and the normal components, as derivatives, dot products and cross products and magnitudes of first and second derivatives of the position vector. So there's a ton of information that we can get straight from the position vector.